Hello everyone, this is Kalpana here. In this video, we are going to see second shifting theorem. Second shifting theorem from Laplace Transform. Okay, if L of f of t is equals to capital F of s. Okay, f of t is a function. Laplace transform of f of t is equals to f of s, which is nothing but L of f of t is equals to capital F of s equals to integral from 0 to infinity e power minus st into f of t dt. Okay, so if L of f of t equals to f of s, and they have given a function g of t which is equals to f of t minus a when t is greater than a, and g of t equals to 0 when t is less than a. Then we have to prove that L of g of t is equals to e power minus as into capital F of s. Capital F of s in the sense L of f of t. Okay. So let's start. Second shifting theorem. So here is a given statement. Okay. Proof. Let L of f of t equals to capital F of s. We know that L of f of t equals to capital F of s equals to integral from 0 to infinity e power minus st into f of t into dt. Okay, this is for t greater than 0, right? Okay. Also given g of t is equals to f of t minus a when t is greater than a, and g of t equals to 0 when t is less than a. Okay. So if you consider a real line, say from 0 to infinity, okay, and let a be a number between 0 and infinity. If t is less than a, then g of t equals to 0. So we are talking about g of t here. Okay, when t is less than a. So in a real line, this is a part where t is less than a. So when t is less than a, g of t is equals to 0. Okay. So when t is greater than a, so right side of a, t is greater than a. When t is greater than a, you have g of t equals to f of t minus a. Okay, fine. Now what we have to prove? We have to prove that L of g of t is equals to e power minus as into capital F of s. Okay, so now consider L of g of t. Okay, now coming to the formula, L of some function equals to integral 0 to infinity e power minus st into that function into dt. So you can write it as integral from 0 to infinity e power minus st into the given function, which is g of t. G of t into dt. Okay. Now, this is equals to integral from 0 to infinity. We split this integral from 0 to infinity as 0 to a and a to infinity. Okay. We'll split this single integral into two integrals. 0 to a is one integral and a to infinity is another integral. Okay. 0 to a e power minus st into g of t dt plus. Now the second part. A to infinity. E power minus st into g of t. Since g of t is defined between 0 and infinity for t less than a and for t greater than a. So we are having two cases. For that purpose, we are splitting the single integral into two integrals, right? So this equals to integral from 0 to infinity e power minus st. So here you are having lower limit 0 and upper limit a. This means t is less than a, right? When t is less than a, g of t is equals to 0. So replace g of t with 0 into dt plus integral from a to infinity e power minus st. When t lies between a and infinity, that is between a and infinity, then for t greater than a, we have g of t is equals to f of t minus a. So here we have replaced g of t with f of t minus a, and here we have replaced it with 0. Good. So this is equals to integral 0 to infinity. 0 into anything is 0 plus integral a to infinity e power minus st into f of t minus a into dt. Okay. So this becomes 0. So finally you'll get integral a to infinity e power minus st into f of t minus a into dt. Okay. So you got L of g of t is equals to integral from a to infinity e power minus st into f of t minus a into dt. Good. So now what we are going to do is, we'll consider this t minus a. Put t minus a equals to u. Here t is a variable and u is also a variable. Okay. And a is your constant. Here a is constant. So if you differentiate on both sides, what you'll get? This implies dt minus differentiation of a is 0, since a is constant, which is equals to differentiation of u du. So you'll get dt equals to du. Okay. So let it be. Now, since you are having t minus a equals to u, from this you can get t equals to u. So now take minus a to right hand side, then you'll get t equals to u plus a. Good. Now we are going to change the limits, lower limit and upper limit. Okay. Okay, fine. When this is for t, right? When t equals to a, then when t equals to a, u equals to, you're having t minus a. Substitute t equals to a here. Then a minus a, which is equals to 0. This means that when t tends to a, then u tends to 0. When t tends to a, u tends to 0. Good. Now, upper limit infinity. U equals to, now apply t equals to infinity. Put t equals to infinity, then you'll get infinity minus a. Infinity is nothing but the extreme number. We don't know what is the extreme number, right? So infinity minus a will be infinity. Okay. So as t tends to infinity, then u tends to infinity. Okay. Good. So now this is equals to integral from a to infinity. When t tends to a, u tends to 0. Or when t equals to a, u equals to 0. Good. Next, when t equals to infinity, u equals to infinity. Next, e power minus s. So here we are changing the total integral in terms of u. So we have to change this t in terms of u. So t can be replaced with u minus a. Sorry, u plus a into f of t minus a is replaced with u into dt. You're having dt here. So replace dt with du. Okay. So this is equals to integral from 0 to infinity e power minus su into e power minus sa into f of u d. This can also be written as integral from 0 to infinity e power minus us into e power minus as into f of u into d. Since we know that e power m into e power n can be written as e power m plus n, right? So we have written e power n plus 1 in terms of e power m into e power n. Okay. So this is equals to here e power minus as is your constant, so you can take it outside the integral. Then you'll get e power minus as into integral 0 to infinity e power minus us into f of u into du. Okay, so this is of the form, since we know that L of f of t equals to capital F of s, which is equals to integral from 0 to infinity e power minus st into f of t dt. Right? See, you can compare this with the actual formula. Then you'll get, in the place of t, you're having u. Okay, so you can write it as capital F of s, since you're having s, or else you can change it in terms of t. So this equals to e power minus as into integral from 0 to infinity e power minus minus st f of t into dt. Okay, since u is a dummy variable, we can call it as dummy variable. So this is equals to e power minus as into integral from 0 to infinity e power minus st f of t into dt. So this is your L of f of t. Okay, by Laplace formula. Okay. So this equals to e power minus as into L of f of t. This L of f of t can also be written as capital F of s. So this is equals to e power minus as into capital F of s. Since L of f of t equals to e power, capital F of s. Okay. So this is your RHS. Okay. So this completes the proof. Therefore, L of g of t equals to e power minus as into capital F of s. So this is your second shifting theorem. So in this video we have seen second shifting theorem. Hope you will understand. If you have any doubts, just leave your comment. See you in the next video. Until then, bye bye.